I'm going to record this class for your review or for people who weren't here and they want to know what we did. And I will link it into Moodle. So I asked you to plot the variables on what's called a scatter plot. So you're going to put X on the horizontal axis and Y on the vertical axis. So it's going to look like that, something like that. I haven't put labels or names on this. I'm more interested in this relationship between X and Y than interpreting right now. So how do you comment? What do you see here? So this is a scatter plot of Y versus X. You always put the Y first, and we are plotting Y versus X. And we see here what would be called a strong, positive, linear relationship. So let's go back. So make sure you can draw that. You've drawn it somewhat like I did here. And you see that the points fall on, you can imagine a line between the points. Now that's not necessarily how data is going to look, right? Data can look like that, but unlikely it's going to be so perfect. This is actually known as a perfect positive relationship. But data usually is scattered. Like something like that, or even more scattered than that. And this is also a positive linear relationship, but you would say it's a moderate one. So that's how you differentiate in words. You say there's a moderate linear relationship. If my writing is ever cut off, let me know, because I'm balancing the camera or your image there. Okay, let's go back and look at the data and see if just looking at the numbers, we can see why it's not like this, but it's like this. Let's do that. So what is the relationship between X and Y? Just looking at the numbers, what do you see?
That the farther you go, the lower it'll get in X. Why?
The higher I go?
Wait, oh wait, no. The opposite, the opposite.
Tell me again. Emilio.
Yeah. What I can see, BCE is totally outperforming the S&P 500.
Yeah, but what
Yeah.
what is the numerical relationship? Numerical.
It's double. BCE is double rate than the S&P 500.
Does everybody agree?
Yes.
Double, right? It's just double. 15 is 30, 9 is 18, and it's BCE is outperforming S&P. So, but this is double. It's perfectly double. The part about being perfect is what puts it on a line, right? It's perfect. It's always double in this data. So what we want to do is represent that relationship numerically. Not because, we can see it, but if it's a little bit off, if it's more like scattered, what can we say? Still, we want to be able to say, like here where there's no data, we want to be able to make predictions or, around the data, but not too far away. We want to be able to make predictions for where the data doesn't fall. And we would be pretty confident to use the line to make that prediction. So there's no data here. So I could use, sorry. Sorry, my ruler. So that'll cross the line there. And so for the data that we don't have, we want to use the line to make the prediction for the value we don't have. Over here, in this situation over here, the other one, notice if X is this value, you have three options, this one, and this one. It's not so clear as here that I would pick this one here. I would predict this value. Here, there's a little bit more variation. So this one is more reliable, okay? So there's two senses we have here. What is the relationship and how good is it? Those are like two different things. What is the relationship and how good is it? And we want to capture that in some numbers. So let's go back to the data and I'm going to show you the numbers and I'm always going to relate back to the graph because I want you to think about visually and I want you to think about numerically, okay? So going back to the data, what I want you to do is take your calculators and I want you to enter this data in your calculator using the stat mode. I'm going to do it with you, but first I want you to try and do it on your own. You see on your calculator, there's the words data and stat. You're going to enter your data on the worksheet called data. So you hit second function data and you begin to enter X and Y in pairs. Keeping in mind you have a feeling for this data, we're going to generate the results. And then I'm going to show you the formula that the calculator is using to compute those results. So I'm going to hit second data. I'm going to clear it because something's in there. And I begin to enter as decimals, 0.15, enter down for X, and 0.3, enter down for Y. Next pair, number 2, 0.09, enter down for X, 0.18, enter down for Y, 0.1, enter down for X, 0.2, enter down for Y, 0.075, and so on. And then I hit second stat. Second stat. What do you see?
Linear.
You guys see my calculator?
Second time.
Let me see. I didn't share the calculator. I did the whole thing and I didn't share the calculator. Okay, so now you should see my calculator. There you go. Were you able to enter it? Should I do it again? I thought you were watching. So second data, and you enter down with the arrow keys and put in all this data. Now for small data sets, this is fine. For the test, this is fine. In real life, you're going to use something like Excel or statistical software. But I'm preparing you guys, as I always say, to use the calculator to write tests. And if you're interested in pursuing finance for the CFA exam, you need to know how to use this calculator. So let's get the results. Second stat, and it says LIN. What does LIN stand for?
Linear. Linear, I think so.
Linear. Okay, so what it's going to do is try and see if the data share a relationship, a linear relationship. Because with a linear relationship, we can make predictions if that is a good linear relationship or a strong linear relationship. Now let's continue scrolling down for the results. N is 5. What does it mean?
Number of
That's the amount of
units.
units.
Yes, the number of units or the sample size. This is the sample size, and that's a internationally recognized symbol for sample size, small n. And then we continue. What is this one?
Average.
Right, so that's the mean or the average of the variable x. So it's 9.9%. So on average, for every $100 invested in the S&P, you get $9.09 back. All right, that's how you interpret that. Let's continue. What's this?
Standard
Deviation.
deviation.
Excellent. So this is the sample standard deviation. The sample standard deviation is a different calculation than the population standard deviation. What's this?
The population standard deviation.
Very
Exactly.
good. It's a population standard deviation. And the difference between them numerically is that the sample will always be larger. The sample size, the sample standard deviation will always be slightly larger than the population because of the formula. The formula for sample is divided by n minus 1. It's 1 less. And it results that the overall value is a little bit bigger than if you divide by n. So I'm going to get into the formulas in a moment. I just want to show you the rest of the data. Then you get y, the sample mean of y, the sample standard deviation of y, the population standard deviation of y, if that's your data. And then you get A, B, and R. What are all these things?
Is that alpha and beta?
Okay, so what do they mean in terms of a line? So A is the y-intercept, B is the what did we
Median.
see? Two was the doubling. The doubling was the slope. That is the relationship between x and y. It's a double. In other words, the slope is 2. And like I said, we're going to talk a little bit more about this. And what is this? You guys don't know. Okay. Anybody know? Everyone see about that before? This-
Correlation.
Very good. We call it the correlation. It's 1. 1 reflects the strength of the relationship. In this case, our relationship was perfect. So 1 is the best you can be. So we're going to review that because it looks like you guys hesitated. This tells you the direction of the relationship, +2. This tells you the strength of the relationship, +1. All right, so let's review what I'm talking about. Let's go back here. So in this exercise, I ask you to take, as a financial analyst provides you with the following ex post data. So ex post data refers to the fact that this is historical data. Every pair gives equal amount of information and is treated the same, right? They're treated with the same weight. In other words, when I average, I divide by the total because each one is equally important. I do that for X and I do it for Y because I need the mean and the standard deviation to be able to calculate the correlation values. And I'll get there in a minute. Statistics is about averages and relative measures. You'll notice this is the average symbol. What does it say? It says sum up all the values and divide by how many there are. This is a Greek letter, capital S for sum. And it's used universally in mathematics to tell you to add these up from 1 through n and divide by how many there are. So whenever you see an n on the bottom and you see a sign like this or symbol, you know it's an average. Let's look here. This is the calculation of S, the sample standard deviation. These are all sample results. What do we see? What's familiar here in this formula? Anything familiar?
Like the formula we've used, like annuity.
No. Francis, that was you? Not
Yeah.
annuity, but what do you see?
I see what I mean. Like every single data you have to how do I say this?
Sum.
No. Well, yeah, it's the sum, but it's the difference between each data and the mean.
Right. So you see the mean. You see this. This is called the deviation from the mean. Every value is subtracted by the mean because what this is trying to do is it's going to get a measure of how spread out all the data is from the expected value. So the mean is the expected value. If you were to bet, if you were to put money or, you're going to put money in the stock market, you're going to bet with somebody about what is going to be the return on the S&P 500 next period, the best guess would be this one, 9.9%. Remember, we got 9.9% for this. But there's some volatility, there's some variation. If we thought the conditions between period 1 and 5 is similar to what we expect, 9.9 would be our best guess or our expected value. But we have to admit, none of these numbers are 9.9. And although 10 and 9 are close, there is some variation. So we want a measure of how variable the variation is. And what we're going to do is get an average of the variation, right? So that's what this is doing. This is taking an average. So you see here, you have the sum again with an n, but not exactly n, but a little bit smaller. Now, if n was 1,000, n minus 1 wouldn't be very different, right? Think of it like that. So, but it matters. It matters in statistics that we take for a sample -1 because statisticians looked at this and they realized that their estimate of how spread out things were using just sample data, just, some observations, not all of the population of data, it meant that they would be off sometimes. So what they decided to do, and they actually proved this with their empirically, like running tests, and it's been easier with computers to do it. They've done it with data that they generate, and they've done it theoretically to show that if you -1, the S will be an unbiased estimator. And that means in repeated samples, the average of the deviations from the mean will actually equal the population deviation, standard deviation from the mean. For the population, if you were to do this for the population, it would look like this. If you had all the data and you use the population size n, you would write like this. But I'll talk about that later. Don't worry about that too much. We'll see this in a minute. But this is saying that you have to divide by n if you have all the data and you actually have the symbol. So the Greek letters are when you have the population of data. When you just have a sample of data, you don't use the Greek letters, all right? So back to here. Okay, so yes, Yariel was saying that this is an average of the deviations of the mean, but it's like they're squaring here. We got to talk about the squaring part and then the unsquaring. So if we're going to square, we have to square root for a purpose, and I'll explain that in a minute. Right now, I just want you to see that this is an average, and keep in mind that statistics is about averages and relative measures. Okay, so this deviation from the mean is like a relative measure. It's relative to what to expect. And it's an average of those squared deviations from the mean is what this is. So notice I say variance here. The name for this is called variance. Right? The variance is the average of the squared deviations from the mean. The standard deviation is the value we actually use. We need the variance to get the standard deviation, but we usually use the standard deviation in reports and things because it is in the same units as the problem. Standard deviation will be in percentage, just like the mean is in percentage. Okay, it's really important. Let me talk a minute about, let me erase this because I'll talk about this later. And let's say we were to carry out the steps here and we actually calculate for x minus x bar all the way down. Can you calculate that for me? So this is 9.9. So you're going to calculate 15 minus 9.9. What do you get? And do it all the way down. So you're just calculating the deviation from the mean. That's what that's called. Okay, how did it go? What did you get for the first period? Anybody?
5.1 on the X.
5.1, good. And it's a percent? And then? Is that correct? Negative 0.9%?
Oh yeah. Sorry.
And then 0.1%?
Mhm.
And then what?
Negative
Negative
2.4.
2.4.
Oh, I'm sorry. I should call somebody. Que Jorge.
Roll number 3.
¿Cuánto?
Which one? Es que what's
Number 4. Sorry. Number 4. Four.
Negative 0.024.
Okay.
Like that.
No, is it? It's just it's point. What is it? Because it can't be it can't be 0.0.
Negative 2.4. It's just that
Yeah, just a percent, right?
he
The
divided by
Yeah, Jorge,
100.
be careful. Yeah, I'm just because I'm writing it as percent. I know it's confusing. Can be confusing. I'm gonna write it as percent right now because I'm trying to make a point. But yes, you should keep it as a decimal. Jorge, you're right. And then this one.
Negative
1.9.
1 point. Jorge.
Negative 1.9.
Okay. Okay. So here we have what's called the deviation from the mean. And notice I calculated x minus x bar, not the other way. Okay. It's not a big deal, but you have to be consistent. X minus x bar. Okay. So these are the deviation from the mean. So what does it mean? When x is above x bar, so when x is above x bar, you will always get a positive. When x is below x bar, you will always get a negative. You see, 9 is below 9.9, you get a negative. So that's the way it's done. So above means this will be positive. A value below will be a negative, which is more intuitive. Now I want you to take the average of these values. What will you get? What is the average of those values? You can add them and divide by 5, or you can use the calculator to do it in stat mode, like I taught you for practice. So if you do that, you have to clear and then start over. And you put the values in here and ask for the average. The stat mode helps avoid data entry issues. So if I put that in 5.1, well, sorry, I can put as a decimal. For this example, I can just enter 5.1. Enter down, and I skip y. I only want one variable. I only want to use one. So 0.9 negative, enter down. I skip y, and then 0.1 enter down, skip y. 2.4 negative, enter down, skip y. 1.9 enter down. Okay, review my numbers. And then now get the average. So if you hit second stat, you can get the statistics for X. Not for Y, but there's 5 observations. And I get X bar is 0. Do you get X bar is 0?
Yeah, I got the same.
So what I'm discussing here, and what I'm getting into, I'm just giving you the highlights of the statistics review. But really, if you're a little bit confused or you feel uneasy or you feel like you need more, go back and watch the statistics review. The point of this is to show you, it's one example, but in general, for any data, the deviation from the mean will always have an average of 0, right? Why? It's all because of X bar. X bar, the mean, is a measure of the center of gravity. It is the point that is closest to all the values in your distribution, in your data set. Let's say this is my distribution, which again, if you don't know what that is, go back and look about what this is. So X bar would be the balancing point. So in this distribution, X bar is here because the distribution balance is right there. So the value that's there will be the mean. And what happens is if I take values above the mean and subtract the mean, the deviations from the mean will be positive here. And the deviations from the mean below, sorry, the deviations from the mean for values below will be negative. And because of, you know, it's just a simple thing. Everyone takes an average, but the power of the average is that it is the value that's closest to all the points to balance the weight over here and the weight over here. Even if you don't have a symmetric distribution, the mean will still act to balance the distribution. So if you have something like this, still the mean won't be here. It will be a little bit more here to balance this tail. This density, it's like the density, which is the value and how many on this side with the density on that side. So the mean will be a little bit away. Sorry. A little bit away here to balance this with this. Okay. And the effect is that the negatives on this side and the positives on those side balance each other. So when you try and average them, you will always get a sum of 0, which gives an average of 0. Does that make sense? Does that make sense? Yes, no? We like the mean. It's not like we don't like the mean, but we have to do something to avoid it becoming 0 because it means nothing. If they're all 0, then there's no unique measure of average deviation from the mean. So what statisticians did, and initially, you know, they just got rid of the negative. Because all they care about is how far the values are, how spread they are. They don't care about one is positive, one is negative. So they eliminated the negative. But then a whole branch of statistics was developed to do something else. What was it that they did? To get rid of the negative, what did they do?
They put it on to the square.
Exactly. You put it onto square. They squared it. When they square, they also get rid of the negative. But there's a price. It's always a trade-off. So you remove the negative, but what happens to the units? Whatever you do to the values, you do to the units. What is 5.1% if you square it? What do you get?
26.1.
26.1. And is that in percent?
Oh, it's 0.1. 0.1.
0.1. Is that in percent? Is that a percent?
Yeah, it's in percent. Yeah, it's in percent.
Or is it something else? Because what I do to the units, I square the units. I have to also do, sorry, what I do to the value, I also do to the units. So the units are actually square. It's like when you do measure, you know, you know, when you say like a 5 by 5 is like 25 square, right? You say centimeter square. It's the same here. You say percent square. Now, nobody talks about that because what they do is they fix it after. What they do is they say, let's square it, but then we're going to fix it. So they square it, they average, they divide by one less for the reason, another reason that I explained. We want it to be a little bit bigger than just divide by n. So we divide by a smaller number. And then at the end, you use the square root. Why? To get back to percent, away from percent squares, because nobody talks about that. No tiene sentido, okay? So that is this formula. Now, do I expect you to use this formula? No, I expect you to use your calculator that I just taught you, because the calculator gives you this, but you need to understand what you got, okay? Where you got it from. It took the variance using this formula, which was the sum of the squared deviations from the mean divided by n minus 1 to take square root to return to percent. Questions for me? So we got some numbers. We got 9.9 for this one. And then we got SX. What was the SX again? Oh, we have to put the data back, but I can do that. So let's put the data back. So it's not hard to do. So 0.15 enter down with y 0.3, 0.09. We're going to make a lot of stats calculations, so this is nothing right now. This is just the beginning. All right, let's see if I did it right. 1.5.3. So it's double. It's always double. 1, 2. Okay. And then I'm going through my statistics, linear results. N is 5. X bar is 9.9%. S is 3%. Usually I'm going to ask you to keep like four or 6 decimals. So you can write that down. This one, we're not going to use it because this is a sample. It's ex post data. It's a sample. Now here are the Y results. This is the mean for Y, the standard deviation for Y. This one, we don't use it. And then we have A, B, and R of 1. There's more data, there's more statistics here, but we're not going to use them right now, okay? We're going to stop there. So what did we learn here? So what we have, what we've done, let me clean this a bit. We want to know about the relationship between X and Y. We see the pattern is linear. You should always make a graph with data first before you make any calculations of statistics, okay? And what we see here is, I'm going to divide the data in half. I'm going to go like this half. I don't know, that's really good half. I'm going to go from the mean. The mean was 9.9, so the mean was like here. So this is, I'm going to divide in half. So this is like X bar here. And then Y bar, what was Y bar? What did you get?
And Y bar is 0.19.
Okay, so it's like here. Okay, so there. Just a rough idea. I'm going to divide the data in half because remember, statistics is about averages and relative measures. So I'm going to relate everything to the expected value of X, the expected value of Y, and what do I see? I'm going to divide the data in 4. When X is above its mean, where do you find Y? Is Y below or above its mean? In other words, when X is high, where is Y? High or low?
High.
High. In other words, when X is high, Y is high relative to, it's all here. The data is here. X is high, Y is high. When X is low, where is Y?
Y is also low because they have a
Right.
perfect,
So just
strong
exactly.
positive
So when
relationship.
X is low down here, you find all the data for Y low below X, Y bar. That's the pattern. So this is called a positive pattern because X is reinforces Y. Whatever X does, Y does too. So when X is up, Y is up. When X is down, Y is down. That is known as the direction or the covariance, how they covary. This is the direction or covariance. And we summarize it in words as positive. So how could what would what would be an example of a negative covariance? Let's see. Let me draw one here.
When one is high and the other is low, or vice versa, something.
Exactly. So when I have something like this, I'm going to divide it in half like I did the other one. Oops. So what do we see? If this is dividing, this was X, sorry. I'm not seeing it properly here. So when X is high, where's Y?
Low.
Okay, so when X is above its mean, Y is always down here below its mean. So when X is high, Y is low. What about when X is low?
When X is low, Y is high. Then the mean.
When X is low, Y is up here. So Y is above its mean. So this is called a negative relationship because they do the opposite. Not necessarily a bad thing. It's not a judgment or anything. It's just that's how we refer to that relationship. This is called negative. Oh my goodness, me and my pen. I'm trying to avoid buying a new pen. I dropped it one class. Okay, so it's a negative relationship because they're opposed. That's different than the concept of strength. Let me show you what I mean. I'm going to erase this right I wrote here. And draw one more graph. Sorry if you're trying to draw all these. You guys can just take a screenshot because I'm scooting everywhere. So what if, and again, all this is discussed in the videos too. What do you call that?
There's no relation apparently. Something like
Something like, yeah, but it's kind of going down, right?
Yeah, it's kind of like a
Trying to make it
negative.
go down. I'm trying to make it go down. Okay, let's do that. Okay, so this is called negative linear relationship, but it's a weak negative relationship. Or you know what? It's not that weak. I can make a one that's even worse. I'll call it moderate. I'll call it moderate because I can make it worse. I just didn't want to get to the no relationship argument. So this is a moderate negative linear relationship. So it's negative because when x is high, y is low. So as x gets bigger, y goes down. But it's not perfect. These are perfect. Because they fit perfectly on the line. I called this one moderate. I call this one moderate. What is no relationship? What does that look like?
When you don't see a pattern like a positive pattern or a negative, you just see like it doesn't have a pattern.
Right. It's not, there's no pattern. It's just like flat all over the place. There's no trend. No trend. Okay, so we call this no relationship. No relationship. Okay. So we understand the idea of direction or covariation, but that's different from how it fits on the line. And we need to clarify those two things. Okay, so let's go back to our formulas. I'm going to go back to our formulas for a moment. That's the notes. I got to go out. Going out. Oh, did you want to take a screenshot in case? I'll come back here as well. So back here, this is the formula of a measure of covariation. Does it look familiar to you?
It's like multiplying the standard deviation of the x and the y's.
Yeah. So if we go, very good. So you can see that if you look here, all these formulas are related, really. You just have to stare at them long enough to see the pattern. Okay. Can I write this one like this? So this is my variance. Right? Square just means dos veces, right? 2 times. So now that you see that, covariance, rather than putting x with x, I'm putting x with y. And what I'm calculating is capturing what I've already discussed. When x is high, y is high, or is when x is low. I mean, x is high, y is low. This is going to pick up that pattern. And I'm going to go back and show you how it works. This is called covariance. Notice we do not take the square root of the covariance. Does anybody know why? Why we don't put square?
Because we're using the percentile, not the squared percentile.
Well, in this case, I do take the square because I want to get to the percentage. So I did take the square root, but here I don't. But there's a reason, a very good reason why I don't. Because covariance can be negative. And you cannot take the square root of a negative number. Right? Because I just told you if the pattern, if the relationship is negative, covariance will be negative. If the relationship is positive, covariance will be positive. Or maybe I didn't tell you that, but that's the idea. Okay. So that's what's going to happen here. So notice what happens when x is high, y is high. Okay, so let's say I take x minus x bar times y minus y bar. If x is high, then y is high. This will be positive. So high, remember, is relative to the mean. So this will be positive. But this one will also be positive. What's positive times a positive?
Positive.
Yeah. So what if x is low and then y is low? This one would be, if x is below the mean, this one will be a negative. And then this one will also be negative. What's a negative times a negative?
Positive.
That's how the formula works. Okay, so if it is a positive relationship when x is high, y is high, or x is low, y is low, you still get positives that sum to give you a covariance calculation that's positive. So in this case, covariance will be positive. What about here? What will covariance be here in this problem? This one.
That would be positive, right? Like
It'll be the
positive and
same.
positive.
Yeah, the tendency will be the same. If I was to divide it up and do this work, most of the time when x is high, let me do the division. I'll show you. Oh. I'm basing this on a measure of the means. So most of the time, most of the data is here when x is high, y is high, and most of the data, even though we screwed up here a little bit, it's not doing it. In general, when x is high, y is high. When x is low, y is low. The covariance there will be positive too. But what happens over here? When x is high, y is low, what happens to the formula? So
It
x
turns negative.
is
Like it's
actually,
positive and a negative.
right. I'm too close to the, I'm too close. Let me undo that. Yadiel gets it. Are you guys getting it? What I'm trying to do here? So when this one is positive, this one is negative, what do you get when you multiply them?
gonna get a negative.
It equals a negative. And the same if one is negative and the other one is positive, you get negative. So that will make the covariance what? Negative. Less than 0. All right, so that's how it works. That's how the shape is translated into a number, or the direction is translated into a number. Covariance will be positive. For a positive relationship, covariance will be negative for a negative relationship. So we've talked about the direction. But what is a number for the strength? How do I notice the difference between this one
Well,
and this one?
correlation.
The correlation, right? So we talked about that. So let's look at that.
I think you begin to see a strong relationship when it is negative or positive 0.7 until I think. I don't know if I'm
So what is the relationship? So this is the formula for covariance. Like I said, you do not have to calculate. I'm going to show you how to get this from your calculator. What your calculator does give you is R. What is R? R is taking the covariance, but standardizing it. It's because from sets of variables to other sets of variables, covariance, the actual value it is not so meaningful. It's not easily interpreted. We use the sign helps us, but the actual absolute value or the value of it, it's not clear what it means. Instead, we convert covariance into correlation by standardizing it. So we scale it down. And when we do that, we convert covariance into an index R. So R is an index. It means it has no units. It's not percentage anymore. It's not percentage square. It's nothing. It's just R. And R is between -1 and 1 for any two variables that are quantitative continuous variables. You cannot do this R calculation for variables that are not quantitative. Okay. And if you don't know what that is, go back to the review and watch it. So it has to be quantitative variables. In other words, you cannot make an R calculation for gender. Like let's say you wanted to make a relationship of a R between the gender of the CEO and the returns or something like that for that firm in the stock market. You can't do an R. There's other calculations, there's other statistics, but not R to do that. Okay. You have to have two quantitative variables, and that's why finance uses statistics, because it's perfect. These are both quantitative values and continuous. So R is an index. So let's go back and let's use our intuition to estimate or, come up with a value. It's a value of what R should be for each of those drawings. Because you guys probably know this kind of stuff already. But let's see. So I told you here, this was perfect. Covariance is positive. What is the R for this relationship?
1.
Exactly, the best, right? R is the best, most perfect, strongest relationship. It's +1 because it's not just 1, but +1. What's this one up here?
-1.
Exactly, -1. So R equals -1. And let's look at these two other ones here. So let's go here. What would this be? Like, give me kind of an idea, relatively speaking. Can't be 1, but it's positive. What would you say you can make it, or it would be if you were to bet on it? Probably positive 0.9 or something like that, or 0.8. Let's say the 0.85, because it's not exactly 1, but when we make the calculation of taking the covariance and dividing by the 2 standard deviations, you're going to get something below 1, but not so close to 0. What would the R be here? This is a little more scattered. Positive or negative?
It would be like the same but negative, -0.85, something like that. Yeah.
Yeah,
Something close to that.
0.8, negative 0.8. And what would you say this one is? No relationship.
It would be more closer to 0 than
Exactly.
either +1 or -1.
R is close to 0. Okay, do I have your guys' attention? You guys get this? This is the main things you need from statistics, the courses that you took for this class. So the direction as captured in the covariance is different from the strength of the relationship. However, they're both going to have the same sign. How do I know that covariance and R have the same sign? How do I know that? How do I know covariance and R have the same sign? Covariance can be a positive or negative. We discussed that, right? It can be positive or it can
Yeah.
be,
Yeah, but
it can be
S
zero
cannot
too.
be a negative. It
But
depends
S
on
can
the
never be a
covariance.
negative. Excellent.
Mhm.
S can never be a negative because it's the square root of something. It will always be positive. That's why R and covariance will have the same sign. S does not affect it. Okay. Now this is the formula for covariance. This is the formula for correlation. This is another variation. These are 3 different ways you calculate correlation. It's in your calculator, you know. You don't actually have to make this calculation, but you should realize these are all the same thing. What I want you to do before we continue, are we done? We're done, right? Okay, so what I want you to do, you guys agree we're finished? I can't believe we use all the time. All right, so what we're going to talk about next week, so you have some time, you're going to have a nice holiday, you're going to come back refreshed. Take some time looking at this document, read this document. If you didn't understand half of what I said today, do the statistics review. You have this week to put it in somewhere, watch some of that. And I'm going to talk about this towards the end, but I'm going to go back and talk about statistics at the beginning because we're going to spend a lot of time, 6 weeks on this. And I want you to be confident about what I'm talking about: mean, standard deviation, covariance, correlation. And then what is the slope? This is the slope. And then look at this. The slope is related back to the correlation. And we're going to talk about that next week. So I want you to feel confident about everything else on here and realize your calculator can give you everything. All these formulas come right out of your calculator for what? For ex post data, historical data. Okay. We're going to spend next class talking about the other kind of data called ex ante data. This data is population level data. So we have all the Greek letters, but I'm going to do my best to show you that these formulas are analogous to the ones up there. All right. So in the meantime, I'm going to put this video on the platform if you want to review it again. Keep me posted if you have any questions. I'm going to work hard to mark your exams and keep in touch, okay, with your questions.
Teacher, when are you gonna put the clave
Oh yeah, I
of
want to
the
do
part
that.
2?
I want to do that soon. Yeah, I should do that soon because I need it to mark your paper. So yeah, it should be soon. Maybe Wednesday.
Okay.
Okay, Arian. Okay, you guys. Buen día.
Sure.
When they
Yeah, buen día.
Buen día, profesora.
Buen día. Bye. Have a nice holiday.